So last time I kind of ended with this slide, and I was talking specifically about how power series behave the way that we would hope that they would behave, namely like polynomials, okay? So you can take derivatives the way that you would think you would be able to take derivatives. The powers basically just come down and everything works well. I mean, you might suspect that because this is a polynomial that never stops, that some, things might change, but they don't, fortunately. The only place you have to be a little bit careful about is at the endpoints of your interval of convergence, all right? So for instance, if I take the derivative of a power series, then look, I mean, you see this? There's like an n that comes down, correct? Okay, right here. Let's see. This thing is having a little bit of a problem. Here we go. Yes. Okay. Why is this this thing not? Ah, there we go. Now it's going to let me use my Apple Pencil. Great. Thank you. Okay. So if you look right here, you can see that, here's this power, and when you take the derivative, that power comes down, yes? Which is, you see it kind of sitting right there, yeah? And what's interesting is, like, that is going to cause the terms to be larger because they're all multiplied by n, correct? And so that could, in theory, endanger convergence at the endpoints, yeah? So one thing that happens is, in the case of taking derivatives, you have to recheck convergence at the endpoints. You may no longer have convergence at the endpoints, okay? So you could, in theory, end up with a smaller interval of convergence, but only smaller in the sense of it might not include the endpoints when it actually did include, one or two of them before. Does that make sense? So you may have to check that. What about integration? Well, when you integrate, of course, the power goes from n to n plus 1, and you divide by n plus 1, okay? And you can integrate term by term, just the way you would a polynomial, okay? But there, you might actually gain endpoints. Does that make sense? Because you're actually dividing by n plus 1, which actually helps the terms go to 0 faster. Do you see what I'm saying here? When you take a derivative, you're multiplying by n, which could make the terms go to 0 slower. When you integrate, you divide by n plus 1, yes, which in theory could make the terms go to 0 faster. So in the one case, in the differentiation case, you may lose endpoints on the interval of convergence. And in the other case, you may actually gain endpoints in the interval of convergence. You see what I'm saying here? So the main takeaway I want you to have is you need to check the endpoints, but the radius of convergence will actually end up being the same, okay? Any questions on that? Because we're going to look at an example here, but any questions on that? Okay. Let's look at an example, and we'll be off to the races here. So here's this thing. I have a power series, and you might say to yourself, well, that's just a power series. Is that actually equal to a real function that's not expressible as a power series? And the answer is yes, because you might recall, of course, we've kind of talked about this at length, but the logarithm of 1 plus x, what was that equal to? Do you remember? X. Logarithm 1 plus x was x minus 1/2 x squared plus 1/3 x cubed minus etc. And what was the interval of convergence for this thing? I equal to, do you guys remember? It was centered at 0, and there was a radius of convergence of 1. Plugging in -1 was bad. Right, so this thing was centered at 0, radius of convergence of 1. Plugging in -1 was bad because you get like the negative harmonic series, which is clearly, you know, negative infinity. But if you plug in 1, you get the alternating harmonic series, which converges. So the interval of convergence here was like -1. You know, you're not allowed to plug in -1, but you are allowed to plug in 1. Okay? So what's the connection between this? So let me just kind of rewrite this thing. Let me move this out of the way so you can see everything in all of its glory here. Okay, this thing, let me write this in sum form. It's like sum in going from 1 to infinity. What? Well, sum in going from 1 to infinity. Help me out here. How would I write this in summation form? It's something over n, x to the n. What over n? Yeah, -1 to the n plus 1 or -1 to the n minus 1 would also work. But maybe it's convenient here to think of it as -1 to the n plus 1. And that will give you the correct sign on each one of the terms. That's convenient here because that almost looks like this thing right here. You know what I mean? Check it out. This is like sum n going from 1 to infinity -1 to the n plus 1 over n. And this is like x minus 2 to the n. Basically, that just looks like all I've done is replaced x with what? X minus 2. Okay, so in theory, this should be just equal to logarithm of what? 1 plus, okay, so how did you get that, Michael? 1 plus. Yeah, all right, so this thing ends up being logarithm of x minus 1. Make sense? Yeah? And before I could plug in, you know, I mean, think about it up here. This right here is saying, right, this right here is saying that I can, like, -1 less than x less than or equal to 1. Well, down here, I'm not like plugging in x, I'm plugging in x minus 2. Do you know what I'm saying? So for this thing right here, you would go like x minus 2, right? X minus 2 is the variable. That needs to be greater than -1 and less than or equal to 1, right? Because after all, you know, x minus 2 is now taking the place of x. So what does that tell us about what values of x I can actually plug into this? Think about it. What would I have to do to everything here? Add 2, right? And if I add 2 to -1, what do I get? 1. So it's going to be 1 less than x less than or equal to 3. You see what I'm saying? Okay, so the interval of convergence here is I equal to 1, 3. Do not include 1. Please do include 3. Okay? Is that making sense? What is the center of that interval? 2. Well, that makes sense, though, because like the powers were in terms of x minus 2. So the center is 2, okay? The center is 2, you know, just to kind of be clear here. The center is 2. The radius of convergence is 1, and the interval of convergence is 1 to 3. Of course, you didn't have to know that this was equal to the logarithm of x minus 1. You could have gone through the whole rigmarole of either using the ratio or the root test and come up with that on your own, right? And then plug stuff in, but I'm just trying to utilize things that we know, okay? So the interval of convergence is 1 to 3, and I am not allowed to include 1, okay? But that makes sense because think about it. Would I be able to plug 1 into the logarithm of x minus 1? No, because that would be like the logarithm of 0. but I could plug in the other stuff for sure. Okay. So let's think about these guys, the derivative, the second derivative, and the integral of this power series, okay? And I want you to kind of work directly with the power series itself, okay? Work directly with the power series itself, but then I want you to kind of think carefully about, okay, what does that say about, you know, this function, logarithm of x minus 1, okay? So I just kind of on your own or with someone nearby, take the derivative, take the second derivative, and think about how that changes the interval of convergence. Yes? I've already promised that the interval of convergence at worst is going to change where? At the endpoints. Yes? And when you integrate, you might gain stuff. Yeah? You might actually gain endpoints. But when you take derivatives, you might lose some endpoints, okay? So, so mess around with that for a minute. Look at the derivative, the second derivative, and the integral, and we'll reconvene and see what you have to say. Okay, let's talk about this a little bit. So we know in the back of our minds that this is logarithm of x minus 1, that the interval of convergence is, what did we say? 1 to 3 or something, right? What's the derivative of this? Help me out here. What's the derivative of this power series? What's going to happen?
So would it be -1 to the n plus 1 times n times the quantity x minus 2 raised to the n minus 1 power all over n?
Yeah, so what would happen to the n's when you take the derivative? They cancel, that's right. So you just end up with -1 to the n plus 1 times, right? The power n comes down and cancels with the denominator n, and you get x minus 2 to the n minus 1, which, by the way, I don't know. I like to rewrite stuff. This is like sum n going from 1 to infinity. Look, I mean, -1 to the n plus 1, that's the same as -1 to the n minus 1, yes? N plus 1 and minus 1, I can move 2 in either direction and get the same sign from that power of -1. So this is -1 to the n minus 1 times x minus 2 to the n minus 1. You see what I'm saying? Yeah? And by the way, I could put both of these under the same power if I really wanted to, couldn't I? N going from 1 to infinity. What is that going to do? Like I could do the -1 distributed to the x minus 2. What's that turn that into? Right, or 2 minus x, right? 2 minus x to the n minus 1. Okay, and look, I mean, really this starts with the 0th power, because if I plug in n equal to 1, it's the 0th power, and then it'll be the first power and then the second power. So do you see that I can kind of shift this whole thing, right? I could really start this thing not at 1, but where? Where does this thing really start? And starting at 0 to infinity, and then I can just write this as 2 minus x to the n power, okay? Now, remember, we said that this was the interval of convergence, and I claimed on the previous slide that you will still have basically the same interval of convergence, except potentially at the endpoints. You're not going to gain anything with the derivative, but you might lose something. So the only danger is we might lose which point? 3. Do we? Think about it. If you plug in x equal to 3, what do you get here? What if you plug in x equal to 3? What kind of a series do we get? It's just -1. I mean, 2 minus 3 is -1 to the n. Those terms don't even go to 0. Do you know what I'm saying? That thing diverges by the nth term test. And there's no chance at 1 because I didn't have a chance at 1 before anyways, yes? Multiplying everything by a factor of n is not going to let me gain convergence at 1, yeah? And besides, if you plug in x equal to 1, obviously you just get this, the series where every term is just 1. That's like adding 1 to itself an infinite number of times. Okay, so what is the interval of convergence for this guy? It's 1 to 3, and neither of those are included now, yeah? Okay, let me rewrite this stuff. You know, I know we just went through some steps here, but I just want to have it all kind of summarized in one place. Okay, so let me clear this. This thing was equal to, of course, logarithm. What did I say? X minus 1. And the interval of convergence here was 1 to 3, including 3. Okay, so 1 to 3, including 3. F prime of x. Okay, let's f prime of x. What did I say? This is sum n going from 0 to infinity of 2 minus x to the n. Okay, and what's the interval of convergence for this? What was the interval of convergence for this guy? 1 to 3 with no endpoints included this time. And here's the thing. In theory, I should have been able to get the same information by looking at the derivative of this guy. Do you see what I'm saying? Yeah? Is it? What is the derivative of the logarithm of x minus 1? 1 over x minus 1. So the question is this thing really equal to the derivative of logarithm of x minus 1, which is 1 over x minus 1? Right? Is this thing really equal to 1 over x minus 1, the derivative of logarithm? Well, think about this. What is this guy equal to? Let's kind of write this out. What is this equal to? Isn't this just 1 plus 2 minus x plus 2 minus x squared plus dot, dot, dot? Hey, what is that? We have a name for a series that looks like that. What do we call that? It's a geometric. 1 plus r squared plus r cubed, etc. Yeah? This thing is geometric with r. What's r equal to here? 2 minus x. Okay? And by the way, 2 minus x, if x is between 1 and 3, 2 minus x is an absolute value less than 1. That's a nice thing, right? Because I know I can invoke the formula for a geometric series. So watch this. This is curious. This thing is going to be equal to, what's the first term? Remember, geometric series is always first term over 1 minus the ratio. Remember that? Yeah? What's the first term here? 1 over 1 minus 2 minus x, which, lo and behold, is 1 over x minus 1. Ah, that should make you feel pretty good, right? This is working out, right? So we looked at this, we looked at its derivative, and then we kind of, in another way, just determined that, yes, indeed, it really is giving us the derivative of the logarithm x minus 1. You see that? So that's interesting stuff for sure. Okay. All right. So indeed, this thing really is 1 over x minus 1. That's good. Okay. But you were supposed to do a few other things as well. Here, let me kind of erase this junk right here. And please, 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 can you kindly, let me erase this stuff. Okay, we've already, no more question about this. We know it's true. Yeah. Okay. could you kindly look at the second derivative also? Okay, and that should be fairly easy to do, given the fact that we just did the first derivative and simplified it down to this. So do the second derivative and figure out what the interval of convergence is. Okay? All right. So what about the second derivative? Help me out here. What's the second derivative? First of all, the 0th power is like a constant, so that basically goes away, doesn't it? Yeah? And then the rest of it's going to be in that thing to the what? To the n minus 1, right? In that thing to the n minus 1. So really, I can kind of start this thing where it's not going to be at 0 anymore because the 0th term is a constant. That goes away. That derivative is 0, correct? Okay. So I can go in going from where? Maybe 1, not, well, from 1 to infinity. Okay, then it's going to be n 2 minus x to the n minus 1. And apparently, this should be equal to, yeah? What should this thing be equal to? Because after all, taking the derivative of that power series should be exactly the same as taking the derivative of that function. Yeah. No, what I was saying was like the 0th power, that's just the constant 1. What's the derivative of that? So that just drops out. Yeah. Okay. What's the derivative of 1 over x minus 1? Yeah, negative 1 over x minus 1 squared. It's interesting. Okay. And what is the interval of convergence? Once again, I'm not going to gain anything. Do you know what I'm saying? Here the terms are even worse. I've multiplied them by n. If I plug 1 in, the summands are just in every time. Yeah, that's really bad. Those terms are going to infinity. Yeah? What if I plug in 3? Well, then it's still bad. It's like n times like an alternating sign of some kind. The nth term test says that both of those series diverge. So what is the interval of convergence here? 1 to 3 again. Yeah? So when you take the derivative, once you lose the endpoints, guess what? They're gone forever. You're just constantly on the interval without the endpoints from that point on. When you take derivatives, that you are guaranteed to at best, keep the same endpoints, but you might indeed actually lose endpoints. Right? Yes, Daniel, you had a question? Yeah. Well, basically, were you just going to say, it seems like once you've lost the endpoints, you lose them for all other derivatives. Yes, that's it. Okay, so what about integral? What about the integral of this thing? Well, potentially, yeah. Okay. So maybe, right? So let's check this out. So if I were to integrate this thing, so let's do that. I'll do this up here, okay? I'll do it in red though, so you can see it stand out. Okay, so the integral of f of x dx, first of all, there's going to be a constant, which is sort of annoying, but I have to just write it, correct? It's going to be a constant plus, what is this going to be? Sum in going from 1 to infinity. Okay, I'll just write -1 to the n plus 1 over, now think about it, if I integrate x minus 2 to the n, what is the antiderivative of x minus 2 to the n? Right? Well, it's x minus 2 to the n plus 1 over n plus 1, yes? And the 1 over n part that's there, that's just a constant, okay? So that just comes along for the ride. So this is going to be n times n plus 1, x minus 2 to the n plus 1. Hey, and do you see that things are even better now? The denominator now is actually bigger, yeah? So now we actually have a chance of having convergence at the endpoints. Do we still have convergence at 3? Think about it. If I were to plug x equal to 3 into that, that would just be 3 minus 2, which is 1. That would go away. It would be alternating, like an alternating thing over n times n plus 1, yes? But the terms without the alternation, 1 over n times n plus 1, those decrease to 0. Since it's an alternating series, I still have convergence. It's not surprising I still have convergence at 3. What about at 1? What about at 1? What do I have at 1 for this thing? If I plugged in x equal to 1. Well, look, if I plug in 1, it's going to be -1 to the n plus 1 times -1 to the n plus 1, which is always +1, yes? -1 to something times -1 to the same something, that's just going to be -1 to, you know, something plus, which is 2 times something. It's -1 to an even power, which is 1, yeah? Okay? So the minus stuff is going to go away, and you're just going to be left with the sum 1 over n times n plus 1. Does that sum converge? Yes. It's basically a p series with p equal to 2. You know what I'm saying? Yeah? Basically, I'm essentially using the, or it's also, it's actually a telescoping sum. If you want to think about it that way, you can actually figure out what that thing is. But the interval of convergence here has expanded. I keep the 3, but I also gain the 1. See what I'm saying? That's kind of neat. Yeah.
I'm confused on how we got rid of the x minus 2 to the n plus 1.
How did we get rid of it? If you plug in 1 for x, what I'm saying is to check it at the endpoints, you just plug x values in. Oh.
I was getting some really
Okay. Yeah, right. You plug in x equal to 1 and x equal to 3. Yeah. So yeah. In the one case, you just basically get a p series with p equal to 2. In the other case, you get an alternating p series with p equal to 2, both of which converge. Okay? All right, does that make sense? You integrate, you may actually gain endpoints. You differentiate, you may lose endpoints. But you're going to have basically the same interval of convergence other than the endpoints. Okay? And sometimes you'll have nice formulas like what we have here. Of course, if I wanted to figure out what this power series actually equals for a given x, I would have to integrate the logarithm of x minus 1, which we know how to do. Do you guys remember doing that? We used integration by parts. Yeah. So that's interesting stuff for sure. All right. All right. Any questions on that before we move on? Okay. Back to, this is going to be the last section we talk about. Oops. What's going on here? I didn't tell you to do that. This is going to be the last section we talk about in chapter 9. Okay. Representation of functions by power series. Okay. This is a more formalized discussion of what we were just doing in that last example with the logarithm thing. Okay. Just kind of recognizing that that we know the logarithm function. So first of all, I want to talk about some of the power series, actually some of the Maclaurin series that we know. So for instance, we know that like e to the x is equal to, you guys remember we sorted this out at one point? It was like 1 plus x squared over 2 factorial plus x to the third over 3. Do you remember this? Okay, and we actually had an interval of convergence minus infinity to infinity for that thing. Yeah? We figured out what cosine of x was, didn't we? That was the even terms kind of alternating. Yes? So it was like 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And remember, the way we found these was by taking derivatives of the cosine function, and we saw a pattern. Same with the exponential. Okay, and this was minus x to the sixth over 6 factorial plus etc. And the interval of convergence here was also minus infinity to infinity. Okay. Let me move this so you can actually see some stuff here. Okay, so there's e to the x, there's cosine of x. Oh, and while we didn't do it formally, we also have one for sine of x. Okay. There you keep the odd power terms and they alternate. Ends up being x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus etc. And once again, the interval of convergence is minus infinity to infinity. Okay. What other power series have we come up with so far? We just talked about one. What was it? Logarithm of 1 plus x, which was x minus 1/2 x squared plus 1/3 x cubed minus, and you see the pattern. There, the interval of convergence was a little different, right? It was -1 is a no-no, and 1 is okay. Yeah? And I'm telling you, we actually know more than this. Because, for instance, we know that, like, what about 1 plus x squared plus x cubed plus da-da-da-da-da? What does that look like? That is a geometric. And we know that so long as the common ratio, which in this case we can think of as x, is less in absolute value less than 1, we have convergence. And if we're at 1 or -1, the thing diverges. Okay? So what do we have here? This thing is equal to the first term over what? 1 minus x. The interval of convergence here is -1 to 1 with no endpoints included. Okay? And there's other things we can do here, like the alternating geometric. 1 minus x plus x squared minus x cubed plus dot, dot, dot. Okay, so what do you think that's going to be equal to? 1 minus x plus, what does it look like I've replaced x by in moving from the first geometric to the one I'm about to write down? What has x been replaced by? Yeah, you've replaced x with negative x. So this is going to be 1 over 1 minus negative x, which is 1 over 1 plus x. What's the interval of convergence? Same. Now I want you to stare at these two guys for a second. Of course, think about it. Logarithm of 1 plus x, if I take the derivative of it, that's just 1 over 1 plus x, yes? Is this power series right here the derivative of this thing right here? Yes. What's the derivative of x? 1. What's the derivative of minus 1/2 x squared? Minus x. What's the derivative of 1/3 x cubed? X squared, et cetera, et cetera. Okay, so you can kind of see that those two are connected to one another by the derivative. Yeah. So that's something interesting that you can take to the bank for sure. And look, these series, I think it's reasonable for me to say that you should memorize them. Okay, so these are 6 sort of critical series. I am, I have benefited hugely by having these in my cognition. Okay, like having these 6 series right here, and let's just be honest. The first 3 are pretty easy to memorize: exponential, cosine, and sine. Really, the geometric one, that's not that big of a deal. And actually, the last one right there, 1 minus x plus x squared, et cetera, that really is just the derivative of the logarithm anyways. Yeah. And incidentally, you could almost just memorize the geometric. You could just memorize this guy right here. Plug in negative x, get that thing, and you could integrate to get to the logarithm if you wanted to, yes? Couldn't you integrate the bottom one to get the logarithm guy if you really wanted to, yes? So integration, so I mean, look, it's not that much to even just memorize 4 of these things, and you could get the other ones from that regular old geometric, okay? Any questions on that? I just wanted to prepare you for what's to come here, yeah. Well, I mean, in theory, yeah, the summation notation is something you should be able to produce from that. Yeah, it's not too bad, but yeah, that's a good thing to have in mind. So, like for instance, let's write that down for e to the x. What is the summation notation for e to the x? What would you write for that? N goes from 0 to infinity, and what would you write? X to the n over n factorial. We did the summation notation for cosine at some point. This one's a little bit nastier. Okay, it's n going from 0 to infinity. How did it go? You remember? -1 to the, oh man, what just happened? Some -1 to the 2n? Or is it -1 to the n? Yeah, -1 to the n. Over, what is it? 2n factorial. X to what power? X to the 2n. Okay. And what about the sine one? What do you think the summation notation is for the sine one? Okay. -1 to the, well, okay, let's do -1 to the n over, okay, this time I want odd factorials, so maybe 2n plus 1 factorial. X to the 2n plus 1. I think that works, yeah? Okay. We've already seen what this one is. This is just some n going from 1 to infinity, minus 1 to the n plus 1 over n, x to the n. And this guy right here, that's easy. This is just some n going from 0 to infinity, x to the n. That's easy. What about this guy? Some n going from 0 to infinity. Let's just make this one really simple and just say it's minus x raised to the n. Okay? Minus x raised to the n. Okay, so that's the summation notation for all of those six series. Okay? But it is helpful to kind of think of them as in their expanded out form. That's a helpful way to think as well. Okay, so those 6 series are key for what we're about to do in this last section. Okay? All right, so I'll let you stare at those for just a minute. But there they all are right there in all their glory. Okay? Any questions on that before we move on? We've seen all of those kind of developed from the ground floor, but any questions on those? Okay? And let's act as if we have them memorized at this point. Okay, let's see if we can do this. So the last 2 sections are kind of the pinnacle of this chapter. It's sort of the reason that we're doing all of this stuff. So we want to be able to quickly recognize and represent functions as power series, because power series are easy to work with. Okay, we've done sequences so far. We've done series convergence. We've done Taylor polynomials and Maclaurin polynomials, which are a special case of Taylor polynomials, yes. Basically centered where? 0. We've done power series. And in section 9 of chapter 9, what's going to happen is we're going to talk specifically about finding a power series that's exactly equal to a given function. We've already done that for cosine of x and various other things on certain intervals. Okay, and again, if you didn't want to work with the entire power series, you can get as accurate as you want by taking enough terms on the interval of convergence. Okay, as we've seen kind of in Desmos. Okay. So again, I'm just repeating things on this next slide, but there are basically 3 methods that you can use. You can kind of come up with a Taylor series by finding a pattern in the derivatives, yes? Remember, you just take one derivative after another, and you find kind of a pattern. You plug in the center and divide by n factorial, yes? Take the nth derivative. Remember this thing right here, if I wanted to have the series n going from 0 to infinity, a n x minus c to the n. What's the formula for a n? What would we have to do? So if f of x is going to be represented by this thing, a n would have to be how many derivatives of the function? N evaluated where? C, and then I would have to divide by n factorial. Yes, we came up with that little formula before. But another tool will be known things from before. Geometric power series are going to be very, very useful. The ones we just kind of came up with, or we recalled on the last, or at the beginning of this section. Okay, 1 over 1 minus x equals 1 plus x squared, etc. And there will be various ways that we can operate with power series. Adding, subtracting them, even dividing power series at times. I mean, think about it. You guys hate things like polynomial division. Guess what we do with power series sometimes? Divide them. Okay? You can divide power series, which is an amazing thing. Okay? So there are certain things we can do with power series that give us more tools in our toolbox. Okay, we already kind of talked about this, but I just wanted to put it on the slides. Remember, if you have this thing, and by the way, we know that there's an even more general formula here, n starting from m, that just makes this AR to the m, so long as the common ratio is in absolute value less than 1. And essentially, a lot of times you can use this to your advantage to come up with formulas for like kind of closed formulas for a power series, and like we did at the beginning of this section, like 1 over 1 minus x is equal to that power series. You could differentiate that thing, etc. But let's look at some examples of this. Okay. So find a power series representation for each expression. So what about the first one? This shouldn't take us very long. What's the power series for this? Sum x to the n, right? So it's going to be 1 plus x squared plus etc. And of course, the interval of convergence is -1 to 1. Yeah? Okay, what about for this guy? 1 over 1 plus x squared. Right, so I could write this as 1 over 1 minus negative x squared, yes? Okay. And then I could basically use this guy up here. Okay. I could use this guy up here and plug in negative x squared in for x. And what are we going to end up with? 1 minus x squared plus x to the 4th minus x to the 6th plus etc. And what do you think the interval of convergence is still going to be? -1 to 1. Okay, of course I can't plug in 1 or -1 into that and get a converging thing. Okay? By the way, when I say IOC, I'm talking about interval of convergence. Okay? What about this guy right here? What about 1 over x plus 2? What would you do to find a power series representation for that? Now, by the way, you could take derivatives of this thing over and over again and try to find a pattern, and then plug in 0 for a Maclaurin series, right? Or I'm basically trying to find a Maclaurin series here, okay? Or, you could do anything like that, but let's think about number 3 together here, okay? So what could I do to come up with a power series for this guy? Well, what do you guys think? Okay, that would work. So if you do that, Michael, what are you thinking here? So if I divide top and bottom by 2, it's 1/2 over what? Or over 1. Okay, let's take this one step at a time. 1 plus x over 2, yes. Have to make it into a power series? Yeah, because it's like 1 over 1 minus r, basically all times a half, right? So this would be like 1/2, right? And then you're going to go 1 plus negative x over 2 plus what? Okay, and in order to do that, what do I need to be true about negative x over 2 in absolute value? Negative x over 2 in absolute value needs to be less than 1, which means that x in absolute value is less than what? 2, if I multiply through by 2, which means what is my interval of convergence for this thing? What is my interval of convergence going to be for this thing? -2 to 2. And do I include the endpoints? No. Okay. Okay, I mean, I could clean this up and maybe write it as, you know, 1/2, right? If I kind of distribute this thing on through, it would be 1/2 minus 1/2 squared x plus 1/2 cubed, 1/2 cubed x squared minus, do you see the pattern here? Yeah? All I'm doing is basically distributing the 1/2 and writing the power of 2 and taking care of the alternating signs and writing down the powers of x. Okay, so that's one way that you would do that one. What about number 4? Do I really need to do any more work to figure out what's going on with number 4? What do you think about number 4? What do you guys think? Well, even simpler than that. Is there really, do I really need to do any more work in moving from 3 to 4? Daniel.
So isn't just like x cubed?
Yeah, why not just think of this as, that's right. Why not think of this as like x cubed times the previous guy? You see that? So what's this power series going to be? 1/2 x cubed minus 1/2 squared x to the what? 4th plus 1/2 cubed x to the 5th minus etc. And what's the interval of convergence for this? The same. -2 to 2, and you can't plug in those endpoints. Okay? You can't plug in those endpoints at all. Okay? Now this one is where I kind of want to start next time. It says make the series centered at x equal to 2, not 0. All of these that we just created were centered where? 0. They were Maclaurin series, basically. Okay? This time, we're actually going to want to create like a Taylor series centered at x equal to 2. The question is, do we have to resort to taking derivatives, or can we just manipulate this thing and then use the geometric series to give us what we want? Okay? All right, that's it.